Previous chapter is the first order study of first order differential equations, right? We studied the qualitative behavior, meaning we found the critical points. We classified whether the critical point is semi-stable, unstable, or asymptotically stable, and we sketched the solution curves, and we solved the first order initial value problems using method of variable separable. We solved it using the method of integrating factors. Then we saw several applications I just listed out a few minutes ago. After that, we studied the existence theory, right? Interval of existence. And I think that's pretty much it. That's the last topic that we studied in the previous lecture. So this lecture, we're going to study solving second order differential equations, ordinary differential equations. So what are the methods that we have in hand? One is the matrix methods. Okay, we're going to spend next 2 to 3 weeks just on matrix methods. Okay, 2 to 3 weeks on that. The next one is, undetermined coefficients method, variation of parameters method. There is something called Laplace transforms method, and so on. Are you with me on that? We're going to study these later, but the next 2-3 weeks is solving the second order differential equations. Second order differential equations using matrix methods. Okay? Yes? And you all have completed linear algebra 1553, 1554, 1564. You're good with that. So bring all your knowledge of linear algebra to the class. We're going to use it extensively. Okay? Now, what is the problem? The problem is pretty much a problem like this. Y double prime plus 3y prime. And y double prime plus 3y prime plus 2y equals 0. Right? This is in the form of y double prime plus p1 of t times y prime plus p naught of t times y equals q of t. Do you agree with me in that? So in here, you can see the coefficient of y double prime is 1. P1 of t is 3, p naught of t is 2, q of t equals 0 always. Okay, always for all t. So this is a second order homogeneous linear ODE. Do you agree with me in that? Okay. Yes. I will upload the notes for you. Trust me, you have seen it. For 2 weeks I've uploaded, so you don't need to write every alphabet that I write. This is like 100 years or 150 years old. I won't cheat you. I promise you. Okay? So don't be busy writing it. Write whatever you like, but don't write everything that I say. That's a second order homogeneous linear ODE. So now the question is, how do we go about solving it? Like I just said, you have several methods. One is matrix methods, non-matrix methods, Laplace transforms, and stuff like that. Okay? But we are going to begin with matrix methods. Why? Because your textbook says so. The second thing is I think is the best justification. There are certain textbooks which doesn't teach you the matrix method. They convert the differential equation into algebraic equation and they find the solutions. But that method is not so effective in my personal opinion. Of course, it's subjective. Matrix methods is very effective. So let's go with the matrix methods. Okay, first. So how would we go with matrix methods? That's the question that we have. So we want to transfer. What did we study in the last 2 weeks? We studied the first order differential equations, right? So the question is, can I convert this into the first order differential equation? It's very natural. I have an unknown problem. Can I translate it into something known problem? Are you with me on that? Anywhere you go, the methodology is the same. I have an unknown problem. Can I map it onto something that I already know? Is that clear? So that's the question that I have. So the effort is to transform the second order homogeneous linear differential equation into the system of first order differential equation. So how do I go about it? I go about it the following way. I'm going to say, okay, because I want to transform it, I want to make a change in variable. And how am I going to make a change in variable? I'm going to say y is going to be x1. Okay? Then if y is x1, then y prime is going to be x1 prime. Okay, the derivative is with respect to t. dy dt is dx1 dt. So y prime is x1 prime. So I want to write this as x2 again. Now x1 prime is x2. So then y double prime is nothing but x1 double prime, which is going to be x2 prime. Is that clear? So now I want to use this. So the first one tells me that x1 prime is going to be x2 and y double prime is x2 prime. So I write that. Plus 3y prime, y prime is x2, so I write 3x2. 2y, y is x1, so plus 2x1 equals 0. Is that clear? So you see, what am I gaining by writing this? I'm getting, okay, x1 prime is going to be x2, x2 prime is going to be negative 2x1, negative 3x2. So you see, I started with a second order homogeneous linear differential equation. I made a change in variable. Okay, this is a change in variable. I made a change in the variable. And because of the change in variable, I transformed my second order into a system of first order. Do you see that? And when I did the system of first order, if you see my left hand side, it is x1 prime, x2 prime. I introduced two variables, so I have derivatives of two new variables on the left side. And on the right side, I want to have the two new variables on the right side. See, in the first one, I couldn't bring in x1, so I didn't bring in x1. But in the second one, I could bring in x1 and x2, so I brought in x1 and x2. Is that clear? If I wanted, I could have written negative. You see, x1, x2 is x1 prime, so I could have written x2 prime minus equals negative 2x1 minus 3x1 prime. No, I want to have one derivative per equation, and I want to have the derivatives for each of the variables, so I had that. Is that clear? So then if you're okay with it, then pretty much I could rewrite this as, okay, x1 prime, x2 prime equals, x2 and the other one being negative 2x1, negative 3x2. I can write this using x1 prime, x2 prime equals, 0, 1, negative 2, negative 3 times x1, x2. I can write this as, okay, x prime equals p of t times x, where my x is going to be x1, x2, my x prime is going to be x1 prime, x2 prime, and my p of t is going to be a 2 by 2 matrix, 0, 1, negative 2, negative 3. So by using the change in variable, I transformed my scalar differential equation y double prime plus 3y prime plus 2y equals 0 into a system of first order differential equation. Is this clear? Yes or no? Yes.
Can't we just, so we found the differential equation x2 prime is equals to minus 2x1 minus 3x2, right?
Yes.
Can't we just integrate that in terms of x2?
Can you integrate it in terms of x2? Is that your question? I'll circle back to that question in a moment from now, okay? Answer is no. Why? Then the next question would be why or why not? That's a perfectly good question. I mean, I'll answer that in a moment, okay? Is this clear so far? So the first thing I want you to do is I want you to notice the difference. X is a vector, x1 is a component, x2 is a component. Do you see that? When I write the components, I write it in a, I don't know how to say, curvy form. When I'm writing it as a vector, I'm just writing it in a normal form. I mean, I don't know how to say it. So this is a vector, that is not a vector. That's all I'm trying to say. Is this clear? So now x1 and x2 are functions of t, are functions of t. X1 and x2 are referred to as state variables. It's just a name. We are not going to use it much in the future. And x is a vector with x1 and x2 is called the state of the system, is called the state of the system at the time t. State of the system at time t. Okay? The next thing I want to remind you is that, okay, I have x prime equals p of t times x plus, q of t. In this problem, q of t equals 0 always. In this problem, so this is a system of, or in other words, this is a homogeneous system of first order differential equation. Do you agree with me on that? Okay. Now here I wrote p of t is in here. P of t is a constant matrix. I mean, constant matrix. Really, there are no functions of time, so I can as well write this as p. So I got p is a coefficient matrix here. There are no functions of t, so it is a coefficient matrix. Do you agree with me on that? Is that clear? Yes? So now, hopefully, this will make you happy. Hopefully. Do you see the similarities if I write it like this? The second line is straight out of linear algebra, right? The transformation from x. And the first one is a system of first order differential equations. So the transformation is the derivative transformation. You see what I mean? So you can bring in, under that notion, you can bring in or unload the whole of linear algebra into differential equations, wherever applicable. Are you with me on that? So now you can see the lines will start to blur. Am I going to teach differential equations? Am I going to teach linear algebra? You will find out that one cannot live without the other. It's just that, like, maybe, if you were born in that era, you would have done 1554 and you would have gone on to discover the whole chapter 3 yourself. But because someone else did it before you, they named it after them. That's all. So now that's about it. So now let's go back to his question, which is we have x2 prime is going to be in this, the question that we had. Okay, not q means it might look like the q term. X2 prime is going to be negative 2x1 plus 3x2. Now remember, whenever you can write this as x2 prime plus 2x1 equals 3x2. So I'm hoping that you are thinking that you want to use the method of integrating factor, but this is not. This is in the form of, you see, this is x2 prime plus p of, sorry. This is not the way I wanted to write. Plus minus 3x2. I'm making so many mistakes. Plus 3x2 equals negative 2x1. So this is in the form of x2 prime plus p of t times x2 equals q of, this is not q of t. Q of t is a function of t only. But here, the right hand side is a function of x1, is in terms of in terms of dependent variable x1. But whereas here, the right hand side is in terms of independent variable t. So that's why you cannot use the concept that you studied from the previous chapter. So you cannot use method of integrating factor on this problem. You cannot use method of integrating factor on this problem. Okay? Not even on the first equation. You cannot do that as well. Is that clear? Are we good? Any questions so far? So what did I do? I wanted to solve the second order homogeneous linear system of homogeneous system differential equation. Using the change in variable, I transformed it into a homogeneous system of first order differential equation. That's all I did. So now obviously I want to next demonstrate how do you transform the non-homogeneous differential equation. So you're going to do the same way. So you're going to start with, okay, let y equals x1. Y prime is going to be x1 prime, which is going to be x2. Y double prime is going to be x1 double prime, which is going to be x2 prime. Okay, so now your thing is the system of equations is going to be x1 prime is x2. Then you get y double prime is going to be x2 prime plus, y prime is x2, so 3x2 plus 2x1 equals sine t. So when you write this, you get x1 prime equals x2. X2 prime is going to be negative 2x1, negative 3x2 plus sine t. Okay? Then you can write this as, write this as x1 prime, x2 prime. The vector on the left hand side has derivatives in it. Then you can write this as x2 in negative 2x1, negative 3x2. Write a vector with the unknown variables x1 and x2 plus the term with just the independent variable 0 and sine t. So the third vector, the second vector on the right hand side are the non-homogeneous term. So you can write this as, okay, x1 prime. I mean, now you can see it pretty much. I'm writing it just as in a matrix form. 0, 1, negative 2, negative 3 times x1, x2 plus, 0 sine t. Now I want to show this is a second order differential equation. So I'm getting a vector. My coefficient matrix is 2 by 2. My unknown function is a 2 by 1 vector. My non-homogeneous term is a 2 by 1 vector. If I have a third order differential equation here, my coefficient matrix would be 3 by 3. My unknown vector would be a 3 by 1 vector. My non-homogeneous term will be a 3 by 1 vector, right? So, and so on and so forth. Yes.
For the x2 is in the column of x1. Are we supposed to write it like that, or is it supposed to be in the second column for x2?
You're asking about this one?
No, the line above. Where we have
Here?
Yeah.
I didn't put a placeholder, but you can write this as 0 x1 plus 1 x2 if you want.
Are we supposed to understand that x2 is in the second column?
I did not write it as a coefficient matrix, so I'm not really writing the matrix yet. The moment I write it as a matrix, yes, it is on the second column.
Okay, thank you.
Okay? Are we all together on this? Now, the other point that I want to tell you is the non-homogeneous term as sine t that always appears at the bottom. So if it is a third order differential equation, then the non-homogeneous term sine t would appear at the third row in the first column, so 3 by 1 position. Are you with me on that? 0, 0 sine t. If it's a fourth order differential equation, then my non-homogeneous term would be 0, 0, 0 and a sine t. Do you agree with me on that? The sine t would be the last term at the bottom, like here. Is that clear? So this is in the form of x prime equals p of t times x equals, not equals, plus, q of t. Plus q of t. Once again, you can see that that my vector x is nothing but x1 and x2. My x prime is nothing but the derivative of the vector x1 and x2. The derivatives are with respect to t. In my p of t, the matrix p of t is going to be 0, 1, what is that? -2 in -3. Then your non-homogeneous term q of t is going to be 0 and a sine t. Okay? This lecture is going to be pretty much setting up the ecosystem, little bit of theory, little bit of computation, everything thrown in. But from the next lecture onwards, it's going to be highly computational, just so that I can tell you. So this is a non-homogeneous system of first order ODE. First order ODE. Why is it a non-homogeneous system? Because Q of t is not equal to 0 all the time. For all t. Because it is not equal to 0 for all the time, that's why this is a non-homogeneous system of first order differential equations. Are we together so far? So what did I do? I didn't do anything fantastic. I wanted to solve the second order homogeneous differential equation. Then I transformed, by using change of variable, I transformed it into a system of first order differential equations. Why am I interested in the first order? Give me some time. In the next 2-3 weeks, I will establish that fact. Yeah.
If Q of t was like say 1 or 2, would it still be non-homogeneous?
If Q of t was 1 and 2, vector 1 and 2, yes.
Like, yeah.
Yes, because it will never be 0, right? So if it is 0 all the time, then it is homogeneous. If it is 0 only for some time, then it's non-homogeneous. Are we all? Yes.
I thought it started as Q of t being equal to 0.
No, okay, I see what you're saying. This problem, the right side is 0, right? So in this problem, the Q of t was 0. Q of t equals 0 always in this problem. In that problem, it was 0. That's why it became homogeneous. But in this problem, it's not 0 all the time, so it's non-homogeneous. So I picked the one homogeneous problem. The next one is I wanted to show how a non-homogeneous problem would look like, so I did that. Okay? Yes.
You basically turn it from a non-homogeneous second order into a non-homogeneous.
No, I showed you what a homogeneous is. Then I thought, okay, I might as well show you what non-homogeneous is. By no means am I traveling from homogeneous to non-homogeneous. I did not. My second order problem led me to homogeneous system. Okay, now that I'm at a homogeneous system, I just wanted to show you how the non-homogeneous system would look like. Yes?
So is that second order differential equation, is that one homogeneous or is it not? The actual
This is the non-homogeneous, right? This is a non-homogeneous second order linear ODE. Why? Because the right hand side is not equal to 0 all the time. So what am I saying? If I have a homogeneous system, homogeneous differential equation, when I transform it, I get a homogeneous system. If I have a non-homogeneous differential equation, when I transform it, I get a non-homogeneous system. That's all I'm trying to say. Yes.
That problem is just a typo.
What is the type?
It says it's homogeneous. Okay.
Thank you. Is that what is confusing you? I seriously apologize. I'm sorry. I'll change it. Okay? Are we all good? Thank you for pointing it out. Good? Okay, now, the thing is that, okay, now this kind of transformation can be extended. So the third order differential equation will have a coefficient matrix 3 by 3. The fourth order will have 4 by 4. So nth order differential equation will have a coefficient matrix of n by n. Right? That's pretty intuitive. I'm not demonstrating it. I'm not proving it. I'm saying it's intuitive. So the next thing is that there is whatever I said so far is what I have written it out. Read it. So So the next thing is I want to really be able to solve a problem like this, okay? Homogeneous system of first order differential equation, okay? Why? Because I mean, just be a little patient and you will see it all. I will tie it all together maybe in 1 or 2 lectures, like maybe at the end of the lecture on Thursday, hopefully I'll tie it all together. You can ask as many questions as you want. You're welcome to ask. I'll answer as many as I can. But then you will see a whole different picture once the Thursday lecture is complete. And I cannot really avoid it because I mean the topic itself is like that. Okay, in here you get, okay, x1 prime is going to be x1 minus 2x2. X2 prime is going to be 3x1 minus 4x2. Do you agree with me on that? So now using this, I can write this as x prime is going to be 1, negative 2, 3, negative 4 times x, where my vector x is x1 and x2, where my x prime is going to be x1 prime and x2 prime. Do you agree with me on that? Yes? So now, I'm sure because of my comment earlier, he asked me that question that's not linear first order differential equation. So I cannot use method of integrating factor. I cannot use variable separable. So I cannot solve it, right? Using the method that I know. Do you agree with me on that? Yes or no? Yeah. So now, but then I want to solve it. Why? Because I mean, see, first order differential equations are the application. You want to study because they're beautiful. Besides that, they are useful in circuits, they're useful in tank problems, they're useful in population dynamics, they're useful in Newton's law of cooling, they're useful in interest rate problems. So because of its application and because of the beauty of the differential equation, you want to study them. So similarly, you want to study the second order because it's applied in several forms. One is the circuits again, finance again, using in the kinetics again because of its applications in kinetics. You want to study them again. So you want to be able to solve this, okay? But now how do we solve it? It's, the methods that we know cannot be applied here. So this is a difficult problem to solve. At this point? I mean, by the end of the lecture, you will be able to solve it. But right now, it is a difficult problem to solve. Are we all together on that? So how do we go about solving it? Luckily for us in 1800s, they solved it for us. So I'm going to just demonstrate that process for you now. Now, to demonstrate that process, I'm going to tell you like a story of, how I think it has happened. So now I'm going to abandon this problem for a moment, for a few minutes, and I'm going to pick up an easier problem. And the easier problem is that. Are you all okay with that? Do you see how I'm jumping very randomly? Okay, just be with me for a few minutes, okay? So this is a system of first order differential equations, but it is easier in the sense that I don't my matrix, my coefficient matrix is 2 by 2, which is easy. And not only easy, but it is a diagonal matrix, okay? Diagonal matrix. So what does that make it? I mean, if you look at it, okay, then I have x1 prime, x2 prime equals, negative 1, 0, 0, negative 4 times, I get x1 and x2. So which will really give me x1 prime, x2 prime equals, negative x1, negative 4x2. Do you agree with me on that? Yes or no? In this one will give me, okay, x1 prime equals negative x1 and x2 prime equals negative 4x2. Do you agree with me on that? This is easy because this is variable separable for us. Do you agree? Okay, just by taking a diagonal matrix, I'm getting variable separable. But my previous problem was not variable separable. It's a little more complex one. So I just I want to solve an easier problem, so I abandoned that one. So I'm picking this. So now if I have this, what am I going to do? Okay, I'm going to say, okay, x1 prime is going to be negative x1. If I make any mistakes, please let me know, because I'm talking loudly and writing, so I'm prone to making mistakes. Then that gives me negative dt, integrating both sides. Then I get natural log of absolute value of x1 t is going to be negative t plus k1. So I get raise it to the e, write it in the explicit form. So that's going to be e to the negative t plus k1. So that gives me x1 of t is going to be e to the negative t, e to the k1. x1 of t is going to be c e to the negative t, c1 e to the negative t. Do you agree with me on that? Nothing complex, right? Nothing complex. Do you all agree with me? Okay. Now, let's go, because it's nothing complex, we are on the familiar territory. Let's go with the other one, which is x2 prime equals negative 4x2. So this gives me the derivative, rearranging the terms. I get this, so integrating both sides. So I get, okay, natural log of that is going to be negative 4t plus k2. The x2 of t is going to be e to the negative 4t plus k2. So x2 of t is going to be e to the negative 4t e to the k2. So x2 of t is going to be c2 e to the negative 4t. Okay, luckily. So if my coefficient matrix is a diagonal matrix, then I can use variable separable method to solve to find a solution. Is that clear? So this tells me one cool thing. What is that? That is my solution x1 of t and x2 of t is nothing but, okay, c1 e to the negative t, c2 e to the negative 4t. Is this what it is? It is, right? Do you agree with me on that? Then the historian said, okay, why do we need to, I mean, see, this is not a surprise. Why? Because we had a second order differential equation. First order differential equation is gives me one arbitrary constant. Second order differential equation should give me two arbitrary constants, and I have two arbitrary constants C1 and C2. So it's very much on the intuitive lines. Are you with me? I've not proved a thing, but it's very much following the intuition so far. So the historian said, okay, why do we have to keep it like this? It doesn't look nice. It doesn't look elegant. So let's make it look cool, which is c1 e to the negative t times 1 0 plus c2 e to the negative 4t times 0 1. Do you agree with me on that? They are trying to separate it out. Then this is the solution of x prime equals negative 1 0 0 negative 4 times your x, where your x is a vector x1 and x2. Do you agree with me on that? So now looking at this problem, specifically coefficient matrix, in looking at the solution, can you draw some parallels or connections, or can you speak something from your knowledge of linear algebra? I'm sure you have it, because every semester people refuse to speak, but after 2 minutes they tell me the answer. Fantastic. Who said that? Very good. And I'm sure, did anyone else think in your head but not say it? So these are eigenvalues, right? The eigenvalues are appearing in your solutions, right? Do you agree with me on that? So what are the eigenvalues here? Negative 1 and negative 4. And the eigenvalues are appearing in the solutions in the exponential term. So if these are eigenvalues, so what could be these two? What does your intuition say? Eigenvectors. Do you see that? So somehow, if we need to check, we will check, okay? But then, so that means what? I had a system of first order differential equations. Somehow my solutions ended up being a linear combination of eigenvectors. Do you see that? Yes or no? Once you realize that, okay, bring in all linear algebra and let's solve some difficult problems. That's all is the goal. That's all is going to happen in the next 2 weeks, okay? But then it's going to be really interesting. But I mean, the shapes of the solutions are going to look cool, and the computations are going to be interesting, and lots of things are going to happen, but essentially the same thing. Okay, so now okay, this being said, okay, now the question I have is, okay, is this a solution of remember, this is x1, this x1 is not the same as x1. Do you see the difference? This one is a vector, this one is a component inside the vector. Okay, so both are different. Okay, so the question is this a solution of that or not? Answer is yes. So how do I check? I mean, if I say x1 prime, then no, let's not do that. So x1 is going to be e to the negative t and a 0. So when I say x1 prime, I'm going to differentiate each of the components. So I get negative e to the negative t and a 0. Then when I find ax1, then I'm going to write this as negative 1, 0, 0, negative 4 times, e to the negative t and a 0. So that gives you negative e to the negative t and a 0. So what can I say? x1 prime equals ax1. So what can I say? x1 equals x1 equals e to the negative t times 1, 0 is the solution of x prime equals ax. That's the first thing. I'm just, because this is the first problem, this is the easier problem, I'm just showing you every possible thing. Next time onwards, I'm not going to demonstrate this, but I'm not going to ask you to demonstrate it, but we are going to have an inherent understanding, yes, it will work it out. Okay, one time you have to see it, rest of the times you can just, based on your experience, you can just say yes, it works out. Okay, are we together? Okay, now the next thing is, obviously not a surprise, is x2 a solution? Okay, again, x2 is a vector. Remember that x2 is the component, so both are not the same, please remember that. So now what is x2? X2 is going to be 0 in e to the negative 4t. So you get x2 prime is going to be derivative of 0 is 0, negative 4 e to the negative 4t. So then the question is, what is ax2? So that's going to be negative 1, 0, 0, negative 4 times 0 in e to the negative 4t. So that gives me 0 in negative 4 e to the negative 4t. So it's not a surprise, x2 prime equals ax2. So x2 is the solution of x prime equals ax. You with me? We just demonstrated it, right? You all good? So now, if they are the solutions, the next thing is pretty much, I can, I'm going to leave it as an exercise for you. So C1 e to the negative t times 1, 0 plus, C2 e to the negative 4t times 0, 1 is the solution of x prime equals ax. Do you agree with me on that? Or do I need to show you? You want to see it one time? Yes, or do you agree? Show or no? You're okay? Okay, good. So this is what it is, okay? The linear combination is also the solution. So what did we do? Okay, so in this problem, my solution turned out to be, I could see the matrix and find the eigenvalues. I could find, how to find eigenvectors. I could find the eigenvectors. They turned out to be the solutions, and the linear combination is the solution. So the next thing that you want to say is, are they linearly independent? How do you check whether two things are linearly independent or not? Okay, C1 x1 plus C2 x2 equals 0, provided C1, x1 and x2 are linearly independent, provided C1 is 0, C2 is 0. Do you agree with me on that? Each of the constants is 0. What are the other conditions that you can think of? Yes?
Like the, I guess like a span, I guess more like, you can like form a span out of curly.
Okay, that's one. What other? There are like in your linear algebra, in your textbook, they will list out some equivalent conditions. Do you remember that? So what is one of the equivalent conditions that you can think of?
Homogeneous?
Has a trivial solution. That's one. What else? Non-homogeneous has a unique solution. Yes. What else? Yes.
Determinant is non-zero.
Determinant is non-zero. Yes? Very good. Determinant is non-zero. So the determinant of x1 and x2 is non-zero means the new name for that is Wronskian. I think it is the name of a mathematician, Wronskian. If I'm fairly right, it is. X1 and x2 is not equal to 0 for all t. For all t, then you can say that x1 and x2 are linearly independent. Okay, set of vectors. So in this case, okay, my Wronskian is going to be e to the negative t and a 0, 0 and e to the negative 4t. So that's going to be e to the negative 5t, and exponential term is never 0. So I can say that, okay, x1 and x2 are linearly independent. Do you agree with me on that? Yes or no? So I had a homogeneous system of equations. So what did I say? X prime, what do we have so far? Negative 1, 0, 0, negative 4 times x. My solution, one of them is e to the negative t 1, 0. My other solution is e to the negative 4t 0, 1. And my general solution is c1 x1 plus c2 x2. And I also know that x1 and x2 are linearly independent. So what can I say? One general name is, so x1 and x2 form a fundamental set. So one is x1 and x2 are solutions of x prime equals ax. 2 x1 and x2 are linearly independent. So I can conclude based on number 1 and 2, I can conclude that x1 and x2 are form a fundamental set of solutions. Okay, clear? Are we good?
Wait, so if the, did you say the Wronskian?
Yes.
Yeah, if that's not 0, then they're linearly independent.
Yes.
But what about the trivial solution? Because like will they? Yeah, they'll meet at t is equals 0.
Trivial solution is always a solution, right? Homogeneous system will always have a trivial solution, like, no interest. Okay? All good? Yes? So now that we solved, okay, what is the summary? So now that we solved an easier problem, so we pretty much got the roadmap for solving a difficult problem. Find eigenvalues, find eigenvectors, write the general solution, sketch the general solution, and go from there. Is that clear? That's the roadmap. In this case, the matrix was diagonal matrix, and that's why I could use variable separable. But when I use variable separable, it was leading me to that place, right? Do you agree with me on that? So now my question is, okay, can I use this roadmap as find eigenvalues, find eigenvectors, and then write the general solution, then sketch the solutions and be done with it. And of course I can verify whether what is that, do they actually satisfy differential equations, are they linearly independent or not. We can do all that, but that's what is the summary here. So that's what is the thing here. So now what happens is a few things. When you solve x prime equals ax, you're going to get few cases. Now case one is your eigenvalues are real and different in positive. Your eigenvalues are real and different in negative. Your eigenvalues are real and different and of opposite signs. Your eigenvalues are real and one of them is 0. The other thing could be a positive eigenvalue or the negative eigenvalue. So these are the real and different cases. Okay. Now the second set is you could have real and equal eigenvalues, but they are positive. Real and equal eigenvalues, but they are negative. That's a second possibility. Then the third possibility is I could have a complex eigenvalues where my real part is positive. I could have a complex eigenvalues where my real part is negative. I could have a complex eigenvalues where my real part is equal to 0. That means purely imaginary. So these are the 9 cases that will arise out of the systems of first order homogeneous equations. How beautiful, right? When we looked at the problem, it didn't really look at all this intense, but it's really turning out to be nice. Right? So the question is, we're going to spend probably today and next class on this one. After that, Tuesday on that one, and Thursday on that one, hopefully. Okay? It's going to be a beautiful experience, hopefully, for you all and for me. Moving on. So let's go back to, so when I have this. Okay, so now what is this step? Characteristic equation, find the eigenvalues, find the corresponding eigenvectors, then write the general solutions. Of course, each of the eigenvectors satisfies the system of first order differential equation. Of course, they will be linearly independent. Of course, they will form the fundamental set, but that goes without saying. Now, this is the even more beautiful part. So now, when your eigenvalues are real and different and positive, I will demonstrate. I'm just giving you an introduction. Like imagine if this was a movie, I'm just showing you a trailer for now. Okay, so now this eigenvalues are real and different and both positive. When they are positive, the solution curves are going away from the origin, and the origin is called a source, and the critical point is unstable. Just like the scalar case, when they're going away from the critical point, the critical point is unstable. When the eigenvalues are real and different and negative, the solution curves are going towards the origin, and that time the origin is called a sink or an attractor, and the origin is a critical point is asymptotically stable. So in this case, when the eigenvalues are real and of opposite signs, the solution curves would look like this, and the critical point origin is a saddle point, and the critical point origin is unstable. Then when you have one of them to be 0, the other one to be positive, you get not one critical point, you get a line of critical points. We're gonna learn all this over a period of next 3 weeks. You're going to get a line of critical point because the other eigenvalue is positive. The solution curves solution trajectories are moving away from the line of critical points. In the fifth case, when the other eigenvalue is negative, the solution curves are going towards the line of critical point. That's basically how the solution curves are going to look like. Okay. Now that we have, I told you what it is. and we are going to demonstrate that for a given problem. Now let's go back to our difficult problem. X prime equals 1, negative 2, 3, negative 4 times x. Variable separable doesn't work. Method of integrating factor doesn't work. But we have a roadmap right now. Find eigenvalues, find eigenvectors, write the general solution, go about sketching the solution. Is that clear? Are you all okay with that? Okay, so now before we go, I want to find what is my critical point. Okay, that's the next important thing for me. So I have x prime equals 1, negative 2, 3, negative 4 times x. What is the critical point for me? Critical point is when the derivative is 0. So that means, ax equals 0. So, what is the, you can see that the determinant of a here is not equal to 0. So A is non-singular matrix. Okay, A is a non-singular matrix. So A inverse exists, and because your A inverse exists, you can write A inverse Ax equals A inverse times 0. So A inverse times A is identity matrix. Identity times X is a vector. This is going to be a 0 vector. In other words, your critical point is really a 0, 0 vector, which means is an origin. Is that clear? First thing I want to get, first thing I want to demonstrate is that whenever your determinant is not 0, 0, 0 is the critical point. Or whenever your matrix A is non-singular, the critical point is the origin. Is that clear? Okay? Okay. So now that this is now that the critical point is the origin, which of the cases is it? Like, I have 5 possible scenarios. Which scenario does it fit into? That's the question that we have. Okay. So now let's go ahead and find the eigenvalues. So I'm sure you. How did you find eigenvalues? A minus lambda equals 0. Determine. Is that what you did?
Yeah.
Okay. You write a determinant of A minus lambda I equals 0. So means you are subtracting lambda from the elements on the diagonal and write the characteristic equation. So this is going to be 1 minus lambda, negative 2, 3, negative 4 minus lambda equals 0. So that gives you 1 minus lambda, negative 4, negative lambda plus 6 equals 0. So that gives me negative 4. So this gives me lambda squared plus 3 lambda plus 2 equals 0. The lambda plus 2 times lambda plus 1 equals 0. So lambda equals negative 2, lambda equals negative 1. So your eigenvalues are real, different, and negative. Are we in linear algebra or are we in differential equations? It doesn't matter at this point, right? We just slice the semesters like that, but it's not going away any soon. Clear? And it'll be interesting if we throw in some amount of physics and finance in it, but unfortunately I don't know it at greater depth. So, you have to live with it, but otherwise it'll be really interesting, what comes out is very nice. Okay, is this clear? So one other way of, see, your A is a 2 by 2 matrix. So the trace here is, you're familiar with trace, right? Trace here is negative 3. The determinant is 2, I think. And your characteristic equation would be lambda squared minus lambda times trace plus the determinant equals 0. So you get lambda squared minus plus 3 lambda plus 2 equals 0. So which will give you lambda equals negative 1, negative 2. So you could go both ways, whichever way, whatever pleases you. Personally, I would, because I'm going to give you 2 by 2. This works only for 2 by 2. So whenever you get 2 by 2, I would want you to go with trace and determinant. because it looks cool.
What does CE stand for?
Say that again.
What does CE stand for?
What stand for?
Like before below the term.
Characteristic equation. Clear? Yes.
What's the trace?
Trace is sum of the elements on the diagonal. So 1 minus 4 is negative 3. Trace is the sum of the elements on the diagonal. Are you familiar with trace? Okay? No, I just want to be on the same page like you. So what is my next step? Find the eigenvectors. You know it now, right? Do I need to teach you how to find eigenvectors? No, you know it, right? So let's go. So, lambda 1 is going to be negative 2. How do you find eigenvectors? You're so shy. Okay. So, A minus lambda 1 times I times V equals 0. So, you solve the homogeneous system, right? Do you agree with me on that? So, in this case, you substitute lambda 1 equals negative 2. So, that gives you what? 3, negative 2, 3, negative 4, negative 2. Okay, this is going to be negative 2 again. Times V1, V2 equals 0. So, you can use addition method, substitution method, or graphical method, or row echelon form, or row reduced echelon form, or Kramer's rule, whatever pleases you. Basically, this reduces to 3v1 minus 2v2 equals 0. So allow me to be goofy for now. Negative 2v2 is going to be negative 3v1. So which tells you your v2 is going to be 3/2 of v1. So you have infinitely many eigenvectors are never unique. But when v1 is 2, your v2 is 3. So that is that, right? So that's a basis for your eigenspace. So when v1 is 2. Do you agree with me on that? Clear? Yes? Is this the way you learned eigenvectors as well?
How did you know that V1 was equal to 2?
How did I know what?
V1 equals 2.
How did I know v1 equals 2?
Yeah.
It's not. v1 can be, it's a free variable, so v1 can be anything. If v1 is 2, then the eigenvector is that. Okay? Clear? So the next thing is, obviously, I'm going to find what is my eigenvector corresponding to lambda 2 equals negative 1. I hope I'm right on that. Okay. So this will give me, substituting, okay, a minus lambda 2 times I times w equals 0. So that means, 1, 2, negative 2, 3, negative 3 times w1, w2 is going to be 0, 0. Okay. So this tells you 2w1 minus 2w2 equals 0. And that tells you w2 is w1. So your basis for eigenspace would be 1 and 1 when your w1 is 1. Right? Clear? Are you all okay with that? Yes? So, if that is true, okay, then you can write your general solution x of t is going to be c1 e to the negative 2t times 2 and 3 plus c2 e to the negative t times 1 and 1. Or you can switch up c1 and c2 as well. c1 e to the negative t times 1 and 1 plus c2 e to the negative 2t times 2 and 3. You can switch it up as well. It doesn't matter which way you write it. Is that clear? Both mean the same. All that I care is C1 and C2 are two arbitrary constants. That's all. Make sense? Okay? Yes? So now I want to show you one other stuff. What is that? So I can, for now, let's say I go with this one, okay? Allow me to go with this one for now. So this tells you that my x1 and x2 is c1, not c1, is going to be 2c1 e to the negative. I'm done with this here. I'm just now, just for fun, I'm showing you something nice. Hopefully you will like it as well. c2 e to the negative t and 3c1 e to the negative 2t plus c2 e to the negative t. So this tells you that x1 is going to be 2c1 e to the negative 2t plus c2 e to the negative t, and x2 is going to be 3c1 e to the negative 2t plus c2 e to the negative t, and x1 is nothing but, you know, from way back. Okay, now I want to be careful here. Because now I'm writing components, I want to switch up my notation. So this is my x1 and x2. From my x1 is y, my x2 is y prime. Do you agree? So y, if you think of it in the physics perspective, y is the position, y prime is the velocity. So when I solve the system of equations, I'm not only finding the displacement, I'm also finding the velocity. I'm not only finding the y, I'm finding the y prime as well. That means I'm not only finding this solution, I'm finding its slope as well. I'm striking two birds in one strike. Does it make sense? Solution and the slope, or displacement and the velocity. Clear? Are you all good? Okay. So the next thing is that, how are we going to graph this? Okay. So now look at it. I mean, you know, if you go back, I got this one, right? This is a scenario where I have two eigenvalues, real and different, both of them negative. So from this, you know, we were expecting that the solutions will go to the origin. We have to see how the graphs look like. We know that 0, 0 is a critical point. It's going to be a sink and asymptotically stable. Okay, so now what are we going to say here? We're going to say the following here. The eigenvalues are lambda 1 is less than lambda 2 is less than 0. So the critical point 0, 0 is a sink, is a nodal. Different textbooks describe it different way. Is a nodal sink or an attractor, and the critical point 0, 0 is asymptotically stable. So we're going to now sketch it and sketch the solution curves and see how it's going to and see how the solution curves are going to go to the origin. That's all that's left. Is that clear? So how am I going to graph it? Remember, I'm going to sketch the eigenspaces first. So V2 is going to be 3/2 of V1. So the slope is 3/2. So the rise is 3 and the run is 2. So you're going to go 3/2 means rise is 3, run is 2, rise is 3, run is 2. So rise is 3, negative 3, run is 2. So I'm going to get something like this. Okay, the rough sketch. This pretty much is my sketch for the eigenvector lambda 1 equals negative 2. Right? Do you agree with me on that? Yes? Yes or no? So the next one is I'm going to sketch the other one. rise over run is 1, so rise over run is 1, rise over run is 1, rise over run is 1, rise over run is 1. So, rise over run is 1, so I go this way. So this corresponds to my eigenvalue -1. Okay. I have 6 minutes, so I don't know if I'll be able to complete or not, but let's see. Okay. Like I said, this is not how. Now, please don't think how am I going to do this problem on the test, because how will you do it on the test is follows from the next lecture onwards. This is like introduction to the concept and understanding in it, and understanding the concept in a holistic way. The how does it appear on the test and quizzes is something that you will see in the next lecture. Okay, so please be patient on that one. So now the question is, the other thing that I want to talk about is, my general solution, right? So if I have x of t is going to be c1 e to the negative 2t and 2 and 3 plus c2 e to the negative t 1 and 1. Do you agree with me on that? That was my solution, right? I think that was my solution, and that was what I was going with, right? Now, what are C1 and C2? C1 and C2 are arbitrary constants, right? So, allow me to choose C1 equals 1 and C2 equals 0. I can choose anything, but allow me to choose the easiest one, okay? Then my solution will become x of t is going to be e to the negative 2t times 2 and 3. So, if you substitute t equals 0, my solution is at 2 and 3. As t goes to infinity, where does my solution go to? Where does the solution go to? 0, right? Very good. Why? Because I cannot write it like this, but if I allow me to just write it for, just humor me for a few minutes. So that means it is going to go to 0, 0, right? Exponentially decaying function that forces it solution to go to 0, 0, right? So that means, what am I saying? I am saying my solution at t equals 0 is at 2 and 3. So somewhere here, and as time goes to infinity, it is at 0, 0. So that means my solution is really inbound to 0, 0. It's traveling inbound, right? It's going from somewhere from the first from a point on this line towards 0, 0 as the t goes to infinity. Do you agree with me on that? Yes? Okay, so now why is it going to 0? It is going to 0, 0 because my eigenvalue is negative. Agreed? Yes? If the eigenvalue was positive, it will go to positive infinity, right? Because the exponential term will grow to infinity. Okay, so now allow me to pick a different constant. C1 is -1 and C2 is 0. So my solution would be what? It is negative e to the negative 2t times 2 and 3. So as when t is 0, my solution x is -2, -3. When t goes to infinity, again my solution goes to 0, 0, right? So this time the only difference being I'm at 2 and -2, -3 somewhere here, and from here I'm inbound to 0, 0. That's all. So my arrows are inbound. Do you agree with me on that? So now it's not a surprise if I have to repeat, like, if I put C1 is 0 and C2 is 1, C1 is 0 and C2 is -1, I would get the same thing for this one as well. These are inbound as well. Do you agree with me on that? That tells you my solution curves are going towards 0, 0. So that tells me that my critical point is asymptotically stable. That tells me that my critical point is a tractor. And it tells me that the critical point is a nodal sink. Is that clear? The only one thing that is left out is how do you graph the solution curve. So for that, I need to really work with my matrix here, A. So if you look at it like, if I put it like, 1, -2, 3, -4, and 1, 0. So what would I get? I would get this as 1 and +3. So that means if you're standing here, you would be experiencing the velocity in 1 and 3 in that direction. Do you agree with me on that? Yes? Yes or no? One positive 1 means 1 unit to the right. 3 means 3 units up, so that means you are experiencing the force in that direction. Are you with me on that? So similarly, now if you are standing at 1, -2, 3, -4, in a point at 0, 1, so then this will be what? -2, -4. So if you're standing here, -2 units to the left and -4 down, so you're experiencing the force in that direction. Do you agree with me? Yes? So those will give me the directions of my solution curve. So if I have 1, -2, 3, -4, and I'm writing it as a 0, -1 and a 0, -1 and a 0. So this gives me -1, -3. So that means if I'm standing here, I'm experiencing force downward. Okay? And if I have 1, -2, 3, -4 times 0 and -1, it gives me a vector +2 and +4. So that means if I'm standing here, I'm experiencing the force in the direction. +2 means to the right, 2 units to the right, 4 units to the top. So I'm going upward like that, right? So based on this, now I need to draw my solution curves. But unfortunately, I'm at 10:45. I have no time. So I'll stop here. I will continue drawing the solution curves in the next lecture. Okay? So that is all I have for now.